So we've calculated all of our different values we need to actually perform an ANOVA, the SST, the sum of squares within, the sum of squares between, and all their associated degrees of freedom. And now the question is, how do we use this for hypothesis testing, or being able to find if there are any statistically significant differences between the three treatments that we have in our example. So first we're going to come up with a null hypothesis, and that is, in this case, that the means of each treatment are all equal to one another, or they don't have an effect in helping you solve your puzzle. And the alternate hypothesis is that at least one mean is not equal to the other two. So at least one of these, like one, might be different from two or three, or just one of these is statistically significant from the rest. And much like when we do our t-tests or our normal or standard normal tests, we're going to assume alpha of 0.05. So the question is, what is the test statistic? We've had test statistics for everything else. What's the associated test statistic for an ANOVA? And so it's what's called the F statistic, which is nothing more than the mean squared error between groups divided by the mean squared error within groups. And what that means is the mean squared error between groups is, let me get to my pointers here. So mean squared between is equal to the sum of squares between groups divided by the degrees of freedom between groups. And the mean squared within groups is equal to the sum of squares within divided by the degrees of freedom within. And so we already know all these, so it's very easy to calculate an F statistic because of what we did in the previous video. So for this case, it's our sum of squares between was 24, our degrees of freedom between was 2, so our numerator is just 24 divided by 2, or 12. And the sum of squares within is 6, and the degrees of freedom within is 6, so the denominator is just 6 divided by 6, which is 1. So in this case, our F statistic is 12. And just to give you a little more of an appreciation or intuition regarding what the F statistic means, note that if the numerator is much greater than the denominator, in which case it is, because it's a number much greater than 1, so most of the variation is between groups, not within them. So that we haven't done any actual tests yet, but an F-stat of 12 would probably suggest that there are statistically significant differences between the treatments we have, because the error associated between is much greater than that within. So let's look at a graphical interpretation and try to compare our F statistic to a critical threshold value on an F distribution. So we're going to define our F critical value as the point on an F distribution where the area to the right of it is equal to the designated alpha of 0.05. And so it's the same as a T critical value. So the way in which we find that is using an F table. So we've been through C tables, T tables, and now we're going to an F table. And this is what an F table looks like. And so I'll show you how to read and interpret from an F table. But it is very similar to finding T critical values, because you have to know degrees of freedom in order to find it. So as you can see, the shape of an F distribution is dependent upon the degrees of freedom between, which is always df1 in these, or numerator degrees of freedom in your F statistic, and degrees of freedom within, which is df2, or denominator degrees of freedom, for calculating your F statistic. So in our example, the degrees of freedom between was found to be 2, and the degrees of freedom within was found to be 6. So what we're going to do is we're going to start in the top left, and we're going to go over to 2, which is our numerator degrees of freedom. Then we're going to go down to 6, which is our denominator degrees of freedom, or our within degrees of freedom. And that value is 5.1433. That's our F critical value. So how do we use this to determine if there's any statistical significance or not? So we're going to show this graphically, and this is an example of what a F distribution looks like. It's definitely not like a standard normal curve, or a T distribution. But all the same properties that we talk about apply the same, where if you take the area under the curve starting at your F critical value and go to infinity, that is your significance. So if we start at F critical value of 5.1433, we go to the right here, that area is 0.05, or our pre-designated significance value. So the area to the right of this critical value is our rejection region. Now let's see where our F statistic lies on this distribution. Well, it's all the way over here at 12, which is far into the rejection region, that starts at 5.1433. Additionally, we can find a p-value from this where we start integrating the area under the curve of the F distribution starting at our F statistic and going towards infinity. And you can see just visually that if we start integrating at 12 and going to infinity, that's going to be a much smaller value than integrating at 5.1433 and going to infinity. So what does that mean? That means that p is less than alpha, which interchangeably means that the F critical value is less than the F statistic. And so we can reject our null hypothesis, which means that at least one of the three treatments is statistically significant from the other two. And again, as a point of clarification, what this is saying is that if we assume that the null hypothesis is true, that the odds of us finding this calculated value in our observed experiment were exceedingly low. Yet we did the experiment a number of times, so that might lead us to think that the null hypothesis should be rejected. And so frequently, whenever you're doing an ANOVA in a software such as MATLAB, what you get as an output is not reject or don't reject. It's frequently a table. And when I took the data and plugged it into MATLAB, it gave me this ANOVA table. And so we're going to kind of step through it and show you how everything works here. Let me get my pointer here. So these 6 values we calculated in the previous video. This is the sum of squares between, this is the sum of squares within, and this is the total sum of squares, along with their associated degrees of freedom. Note that 24 plus 6 adds up to 30, and 2 plus 6 adds up to 8. So this all is still very similar to what we saw before. And then the next column, the third column here, is the mean square error. So there's a mean square between and the mean square error within. And all that is for between groups, it's 12 is 24 divided by 2, 12. 6 divided by 6, which is 1 for within. So this is the numerator and the denominator of your F statistic, which moves us to the next column. That if I take the F statistic is the mean sum of squares between over the mean sum of squares within. So this value of F is nothing more than 12 divided by 1. That's 12. And lastly, this P greater than F value, this is your P value that's associated with your F statistic. So that area under the curve that we outlined before, so if this is our original curve, and this is where 12 is, the area under the curve to the right of that is 0.008, which you can see is much less than 0.05. Which again shows that P is less than alpha, and you should reject your null hypothesis. So there are some limitations to the ANOVA, namely that it can only tell you if there is a statistically significant difference between groups. It cannot identify which ones are statistically significant from one another. So whether treatment 1 is different than treatment 3, or treatment 2 is different than treatment 3, or so on. So it just tells you globally whether there is a difference. And in order to glean more, you'll have to do subsequent, what are called post hoc tests, to figure it out. But hopefully this video has allowed you to see through a simple example how to do an ANOVA. And while the data sets can get much larger, the basic skeleton remains the same. So hopefully going forward you'll be able to use this when doing multiple comparisons.